So when we looked at this pattern over here, and I have an electron coming into this field this way, what path is it going to take? It's going to be circular, right? The very first piece here, so it's going into the page and the electron is moving to the left, right? That means that it's going to get deflected up. As we look at it when it's deflected up, we see that it's deflected this way. And it just goes around and around. So we get this circular path. Well, way back in Physics 20, for a brief period of time, we learned this. Do you remember what that guy is called? Force centripetal. Going around a corner. Okay? They're going to be equal to each other. How do we find, in the most basic form, how do we find force centripetal? F, whoops. No, not F. M times AC. How do we find in its most basic form force magnetic? We just learned this yesterday. As long as it's perpendicular to the magnetic field, right? If it's parallel, then it's not going to happen. All right, let's get more complicated. If I'm looking at velocity, how do I find AC? Looking on your formula sheet, how do I find AC? V squared over R is equal to QVB. Okay? This R here is what? If it's centripetal, that R is going to be radius. Okay? So this is going to work for any problems that are dealing with radius. Okay? It's going to work for any problems where we are dealing with radius of a curvature for charged particles in a magnetic field. If I wanted to look at R as my responding variable, it would end up being isolated like this. R is going to be equal to mv squared over qvb if I wanted to isolate for R. And what do I see about my velocities? Cancel one out on top and the one on the bottom. So R would be equal to mv over qb. And we can come up with three different kinds of relationships of radius. Radius is proportional to m. Radius is proportional to 1 over the charge. So as the charge gets larger, radius would get smaller. And radius is proportional to velocity. So 3 different kinds of relationships there. Okay? So what does that look like when we're dealing with a question? An alpha particle. I'm going to start highlighting key pieces of information. An alpha particle enters a 1.2 Tesla magnetic field, causing it to turn with a radius of 2.34 centimeters. Determine the speed of the alpha particle as it enters the magnetic field. I don't know why it's going in and out of focus. Figure your life out, camera. All right, some key pieces that we know about an alpha particle. If we were trying to determine a direction, this would be the right-hand rule because it's a positively charged particle. An alpha particle, we know 2 pieces of information. We know the charge, which is and we know the mass. So those are some key pieces of information we know with just words. They're not even numbers in the question. We know the magnetic field strength is 1.20 Teslas. And we know that it turns with a radius of 2.34 centimeters. And it's asking us to solve for speed. Base unit in physics is meters. 0.0234 meters, right? 2.34 divided by 100. It's asking us to solve for velocity. We know that velocity comes from, that formula. But because we're talking about turn with a radius, force centripetal is equal to force magnetic. We have mv squared over r is equal to qvb. We've already shown over here that when we have a relationship in this, we're down to 1 velocity. Okay, so this is going to be the v here that we're solving for. Okay. Yep. It's just practice problems from here on out. So what do we get for a value? Okay, do we need a direction? No, because why? Because it's speed, so it's magnitude only. We don't need a direction. Okay. A particular lithium sample. What does lithium tell me? What's the charge of lithium? 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 You guys are the ones with the chem data booklets. Lithium is 1 plus. Okay, how is it that you have me questioning? These isotopes are singly charged in an ion generation and acceleration chamber. Since individual atoms are ionized at different points in the acceleration chamber, their speeds vary when they enter the velocity selection chamber. In the velocity selection chamber, the electric field strength is 5.95 times 10 to the 2 newtons per coulomb, and the magnetic field strength is 1.55 times 10 to the negative 3 teslas. The velocity selection chamber allows ions of a certain speed to pass through undeflected. Okay, we know that that tells us something. The beam of undeflected ions then enters the ion separation chamber where the magnetic field of 0.185 Tesla splits the beam into two beams. Beam 1 curves through a radius of 0.131 meters. Curves through a radius. Okay, and this is a picture of what's going on. So we see that it comes in through the electron chamber, it goes through the velocity selection chamber, and then it goes through and you get beam 1 and beam 2. The speed of the undeflected ionized lithium ion, which is a 1 plus charge, as they leave the velocity chamber is, the answer is going to be B, but this is how we're going to get to it. We're going to do this big fun math. On this next sheet, you should have a blank page. So this is the question. Don't go too far away from it. Let's do some pieces of information that we know. Lithium has a 1 plus charge on it. That means that its Q is 1.6 times 10 to the negative 19 coulombs. It's one elementary charge. Okay, lithium 1 plus. It says in there that the electric field strength was 5.95 times 10 to the 2 newtons per coulomb. It says that it enters the first magnetic field with 1.55 times 10 to the negative 3 teslas. It goes through, does its whole path. It goes through another magnetic field, and it is 0.185 teslas. And it has a radius of 0.131 meters. It asks us for the speed of the undeflected ion. Okay? So we got a bit of a pathway to go through. Velocity is going to come from this piece here. That's where that formula for velocity is. Now it's talking about an undeflected. So in this particular piece, we have at play, we have coming out of here, we have force magnetic, and we have force electric. It is a positively charged particle coming in here. If this is the positive plate, which way is force electric going to go? Down. force electric will go down. Force magnetic, it's going to go up. Okay? So we're going to have force magnetic plus force electric is going down, so it's negative. And then what's always working downwards towards the center of Earth? Force gravity. However, when we look at it, this is an atomic level charge. So force gravity is 0. Or it's not 0, it's negligible. Okay? Because it's an atomic particle. In this piece, multiple times, it says undeflected. Whoops. Says undeflected there, and it says undeflected in the question, which means that force net is 0 because it's undeflected. So now we have force magnetic being equal to force electric. How do we solve force electric when we have this piece of information over here? EQ. And how do we solve magnetic force? QVB. Okay, it's asking us to solve for velocity, EQ over QB, and we see that the charge cancels out. So it's electric field strength over magnetic field strength. And it's asking, it says here, how do I know which magnetic field strength to use? It's leaving the velocity selection chamber. Okay? And it says up here, in the velocity selection chamber, the electric field is 5.95, the magnetic field is 1.55. That's how I know which of those two to use. So, because the question itself is asking us, as they leave the velocity selection chamber, and up in the question it says, in the velocity selection chamber, the electric field strength is 5.95 times 10 to the 2, and the magnetic field strength is 1.55 times 10 to the negative 3. That's why I know to use that one instead of the 0.185 that's in the ion separation chamber. Okay? Location, location, location. So my velocity becomes what? Did you get that, Cadence? Perfect. Okay, so we got the first part. The second one says the mass of a lithium ion in beam 1 expressed in scientific notation is A point B times 10 to the negative CD. So it's asking us for point value times 10 to the negative, and it should be a 2-digit number. Okay, that's what it's asking us for. It's asking us for this answer format. So how am I going to find the mass of ion in beam 1? Well, by the time it's here in this chamber, it's going around a curve. It's being deflected out, okay? So I know that force centripetal will give me my mass, right? But I don't have all those other pieces. I do know this, force centripetal is equal to force magnetic. These velocities are the same. Question, Kyle? Yeah. These velocities are the same ions, so this one's going to cross off and that one will remove one. I'm looking for mass. Q, B perpendicular R divided by V. That's how we're going to solve for velocity or mass. Now this particular one, this piece here is the ion separation chamber. And in the ion separation chamber, my magnetic field is 0.185. So that's the B2 that I'm going to use. I'm going to use the 3.84 times 10 to the 5 that I calculated because that's the speed it was leaving the velocity selection chamber at. Bless you. What do I get a value for mass? Okay. 1.0. I would give you 1.01 because Q is a constant. I would give you 1.01. Yeah, the charge varies. Some books will do just 1.6, some will do 1.60. So it's more common to see it as 1.6 times 10 to the negative 19 or 3.2 than to get that second decimal spot. But again, it's a constant, so we don't use constants when we're doing significant digits. Oh. No, thank you. Thanks for asking. Okay. So when we take our answer, Daniel said 1.01 times 10 to the negative 26 kilograms. When we go to write our answer into a diploma, this A point B times 10 to the negative CD is going to be A point B times 10 to the negative CD. So 1026. So it's kind of a good check. When you go to do your answer and it doesn't fit that format, you get a positive number or you get only 1, like times 10 to the negative 3. It's a kind of a good check. You're like, or it's a good check. Okay. Here's another one. The more practice we can do, the better. Okay. Oh, I was hanging really. Oh well, we'll start from here. 4.4 to 4 times 10 to the 4 divided by change in V times the charge. We got 3.2 times 10 to the negative 16 joules. That's right here.
I thought it said.
That's okay. Did you get a radius value yet? Okay. The other ways is we can say either or. Okay, I'm just going to zoom out because I forgot to record this thought process. So I will zoom out so they can see our pathways. Yep. Okay. I'm going to leave the last one, the cyclotron one, for you guys to solve. The answer is in Google Classroom inside the teacher notes. But let's just look at this one for, I don't know if I have it printed off. Let's just look at this one because there's some concept questions that go with this one. Okay. It says, a cyclotron is a particle accelerator that is constructed of two hollow metal shells shaped like Ds in a perpendicular magnetic field created by magnets, as shown below. The entire apparatus is placed in a vacuum. An alternating voltage is maintained across the D separation. Positively charged particles. Positively charged particles, such as protons, are injected near the center of the Ds and travel in a circular path caused by the external perpendicular magnetic field. The frequency of the alternating voltage is adjusted to increase the speed of the particles each time they move across the D's separation. This is way back when you actually had to write out your chemistry, way back when I had to write a diploma. You had a written response. One question worth 15% of your test. Determine the direction of magnetic field needed to cause protons to circle in the direction shown. So we want it to circle in this direction. Okay? So it says, determine the direction of the magnetic field needed to cause protons to go in a circular direction. Well, first things first, which hand are we going to use? The right hand. Because it's a positively charged particle. Okay? So, what do you say? Which way does it have to go? Well, the answer's on the sheet already. The magnetic field has to go up because we want it to go, the Are injected near the center. So their injection point is right here. And so if I want it to circle this way in a path that goes like this, right? I want it to go this way. My magnetic field is going to go up. So that you get that circular motion.